Ladies and gentlemen, welcome to the Ryan Ride Mechanic channel. How the heck are you doing today? Alright, today's video. This roller coaster might make or break your day depending on your opinion, so I want to get into it. It's those three little letters that a lot of us either like or cringe to hear. I'm going to talk about how the SLC works. Let's get into it.
Now get ready. Here we go.
Alright, if this is your first time here, welcome. I appreciate you watching the video. Like, subscribe, do all that stuff downstairs. It does help me out. I do appreciate it. Keep coming back for more videos. I have plenty of them. Let me know what you want to see, how it works, and I'll try to make a video about it. Eventually, I'll get around to them. Alright, today's video, I am talking about the SLC, the infamous Vekoma SLC. The SLC stands for... Wow, mine just blanked right there. Wow, that was crazy. The SLC stands for Suspended Looping Coaster, or it could be an acronym from the park. Could mean Shitty Looping Coaster. It all just depends on your point of view, really. I've heard it called a lot of other things, but the SLC was manufactured by Vekoma. It's a very popular ride. It sticks around, and it's a good asset to the park. Why? Because they're what I consider to be a twisted metal steel coaster. They're really fun looking from the outside. Most people, once they see the SLC, they're like, yeah, let's go on that one. That's going to be cool. And that's a good asset to the park. It's a good thing to have. Vekoma has done numerous things for this ride. They've redesigned the track layout multiple times. They offer new trains for it, which is a really good thing. So you can buy, when you buy an SLC, you can buy the trains with multiple variations. You can buy the original style, like I was used to taking care of. You can upgrade main axle housings, chassis, frames. You can get it from a singular backbone down the center to a dual backbone. You can get them with restraint vests. All sorts of upgrades you could do to these rides in the purchasing process, even afterwards. Vekoma pretty much offers it for everything. Okay, so let's talk about how these rides are set up. All right, first thing we're going to go into, it's either trains or track and structure. Which one to do first? Let's go with the track and structure. Okay, so the track and structure is Vekoma's older style. This is the old Aero style track, but it's basically upside down. It's two rails inside of a C shape like this, so you have the two rails there, and that's where the train rides. Now, this is an older style of manufacturing, and the fabrication process of the rails leaves some tolerance to be desired. It's not a particularly great thing. The rails with the external, where they're supported in the center, offer a far superior ride to the old style C-channel rails that the SLC does use, and the precision's much more, it's much more tolerable all the way down. But we could talk about that at a later point in time. So the track is divided up into block sections. For those who don't know what a block section is, this is a section where any vehicle can go into it, and that section will prevent another vehicle from entering that at the same time. So it's basically like a red light, green light that prevents vehicles from bumping into each other or slamming into each other out on the track. The blocks on this particular ride, I'm going off the one I remember I used to work on. So the blocks for these rides are set up into 4 blocks. It runs 2 trains, 4 blocks. That's the typical ingredients. You need 2 blocks for every 1 train generally. I know some of the rides moved that around a little bit, but it was into 4 blocks. So you started with the block A, or the station block, and then you move on to block B, which was the lift hill. Block C was everything from the very top of the lift hill all the way through the service brakes, And then block D was the trim brakes out behind the station. The tracks are also mostly equipped with a transfer track that hangs off to the side. The track can be positioned either way. I've seen 1 or 2 parks, one that comes to mind, where they inverted the transfer track and had it actually go forward. But interestingly enough, the station where you start the ride is all manufactured by Vekoma, which is kind of unusual. Normally the ride manufacturer just produces the station as in like, here's the track, here's the components like that. But Vekoma actually made the entire station, all the structure and everything up there that you currently wait in line on up there. So that's interesting. Brakes for the ride. The brakes uses Vekoma calls them an L2 style brake. The L2 brake, if you're familiar with the older Aero Vekoma rides, the L2 brake is these guys. This is an L2 brake. So this is a linear style pinch brake. They work just like that. The Vekomas, the SLCs, inverted coasters in general, on the underside of these brakes, they have these little tabs that hang over here and here, and this allows the brake to hang upside down and still function properly while it's upside down. But these little tabs on these brakes are prone to breaking off from time to time. Now, that's not the only thing holding them up there. There's also more tabs along the inside. This one I don't have fabricated that way. But there are other components that hold the brake up there, not to mention the springs on the outside kind of retain the whole assembly. As a service bulletin, Vekoma came out and said to modify these brakes a little bit and add another bracket to them in case these end brackets broke off like they commonly did, so the ski wouldn't fall down so far, because if they fall down just about this much. But if they were to fall down, it could basically break parts of the anti-rollback. So the anti-rollbacks on the train, that is. So they used bladder style brakes, and yes, they are the old Vekoma style, Aero style brakes. So basically these brakes, just like this sits right now, these brakes fail open. They need air pressure to close, and you release the air pressure, they spring open. Now, the safety of that is up in the brake assembly above the track. Above the track there is a service panel that has a 5-gallon-ish air canister up there with one-way check valves in and out, so that if you had a power failure, all the brakes still had air pressure. Even if you blew a brake line apart and you lost all the air in the entire system, all the brakes would still have plenty of pressure in those canisters backed up. A lot of people say, oh, that's really weird that they're fail open. That is really weird, but you know, the entire time I've worked with those things, never heard of one actually failing, coming apart where it's like it released the train. Now, that does make for some odd service things, because while you're working on a train out there, if you lock the ride out, the ride will eventually bleed all of its air pressure off. Now, the safety system for those brakes is that if you have a catastrophic air failure, they're guaranteed to hold the brakes closed and shut for 20 minutes. After 20 minutes, theoretically they could open. So one of the tests to do on a weekly is actually to do a bleed down test on the brakes to make sure that they don't open. So what you do is you build the air system up to its normal charge, you shut off the air tank, and then you go out to the brakes. And typically there's a ball valve mounted somewhere. Ours is on the very end of the trim brakes, or the service brakes. And you would open the ball valve up and drain the entire line of all of its air. And then you start the timer. And basically underneath you'd go through and you'd watch to make sure that the brakes don't open up. Now, the funny part about these brakes is that since all the valves on the components are piloted, which means they need air pressure to maintain the valve, they actually needed about 35 psi to maintain the pressure in that valving assembly. So it wasn't like after the 20-minute breaks, after the 20 minutes, you weren't going up there looking for like, maybe there was a small gap on a brake, or maybe one side was open a little bit. If you have a brake fail, and I've had a couple fail while I was working on them, typically because there's an air leak in the assembly. But if you have a brake fail, you'll be sitting out there not paying attention, and then at the 16-minute mark, you will hear one of the brakes just go psh and open up, because the valves that were holding in that position suddenly, just once they drop below 35 psi, they just spring back open, and then they exhaust the air that's in the brake opens right up. So they're really easy to tell when they fail, because you hear the air come out of it, and then you'll see one brake open up, and then it's like, okay, here we go. To work on those brakes on a daily basis, you typically either need a platform built underneath the brakes, which some parks have done. They've built a platform underneath there. Or you need a man lift or a scissors lift to go underneath there and to get up to those brakes every day to inspect them. You have to do the normal stuff. You have to inspect the liner. You have to inspect the welds around it, the hardware, air lines coming in and out. Everything has to be secure, tight. Holding air pressure is one of the big ones for every brake assembly. Now that ride, the main reduction brakes have 10 of those brakes in a row, and then the next, which considered like the trim or the holding brake over there, those are only 4 brakes on that one. As you roll around that corner, we come to the transfer track. The transfer track is like a lot of old Aero Vekoma style tracks, which is where they have the normal run track underneath in this case, and on the top there is 2 curved rails that sit off to the side. And then as you open the locking pins up, the locking pins unlock, and then that whole track assembly rotates around, and then those pins lock back in place. And at that point you have open track to one side, and then you could transfer the train from the station back into the transfer area on the other side. Now, my particular model did not have any sort of automation when it came to that transfer track assembly. So we had to be very careful because you could move the train back and there's a set of stops at the end of the track. But you could move the train back and run it into those stops. And if you did run it into those stops, those booster motors are very powerful. So if you ran it into the stops, it would actually damage the wheels, and then you'd have to pretty much take the wheels and axles off and everything and NDT them afterwards again to make sure nothing is damaged, like cracked or broken. The wheels were pretty much a write-off at that point. It was safest just to throw those things away. Now, outside of the transfer track, all along the transfer area and into the station, there are pairs of booster motors. These are stationary, non-positionable booster motors throughout the majority of the track, except for right in front of the transfer track. Those motors were open. We actually had pneumatic actuators that allowed the booster wheel gap to go from 0, where there's supposed to be no gap between those wheels, and then they opened up to allow about a 10-15 millimeter gap for the train to pass through it. Now, our particular model, we actually did a modification on it a little ways into its service life, and we actually made it to where when you dispatch the train from that trim, that D, or the very last set of brakes, into the station, those booster motors closed and helped drive the train in. Now we did that because one of the things that almost every SLC has is that when it goes into the last corner and makes that hard right-hand turn into the station, it really gives you a jar to the left. Like, nobody likes that thing. You could stand around that corner, and every time the train comes around, you could just hear it go, ooh, ow. Everyone's like, ooh, ow, 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 as that train comes around that hard 90-degree corner. So what we did is we adjusted the booster wheels outside really tight, and we used the ones on the outside of the transfer area to actually slow and help feed that train around that corner constantly. Actually, after about 2 years, the park pretty much gave up on those motors because we were constantly adjusting them and they were constantly out of tolerance, and it was just too much work for them. So I was like, okay. Now, I have a feeling on newer SLC models, you could opt to retrofit with the eddy current brakes, magnetic brakes. That would work fine for those. They still require pinch brakes to make the blocks because, remember, magnetic brakes can't actually stop a train. And from the time you get into those brakes all the way into the station, both of that main brake section and the trim section are at a 4-degree downward slope. That helps when the brakes release. That's the reason the train advances forward, because it's always at a downward slope. And it runs the train back around those 2 corners back into the station. Now, in the station, it's a really simple assembly. There's not much inside there. All you have is 3 brakes that are the primary source of stopping for the train, and 8 booster motors, which are the booster motors that are going to be necessary to help feed the train into the station, stop it, and start it to get it to go back onto the lift. The station is equipped with a platform that goes up and down. I know people at home are like, no, it goes left and right. Really? It goes left and right? No, it does. It just goes up and down. The platform is like most platforms out there. It is counterweighted on the underside. So you have two very large hydraulic cylinders on the front of the platform that raise and lower the platform. And then on the underside where the pivot is, the underside of the platform has a large counterweight that goes up and down along with it. So as the platform curls back down, the counterweight comes up. So if you remove air pressure, broke a hydraulic line, did anything like that, the platform would simply return to its full upright position, and then it would be safe to unload. You want to be a little careful if you lost all function of the platform, because theoretically if everyone stood on it at the same time, you could get it to go back down. I've actually been there and done that before with a bunch of mechanics. We were actually trying to push it with no air pressure and we got the platform to go down. It's nothing life-changing. You're just like, oh, the platform went down. So it's not a big deal. The platform, I said, it's got two big hydraulic cylinders in front, but it's actually pneumatically operated. So it's kind of an interesting thing. It's an air over hydraulic system, which is kind of odd. So in the front of it, there's one of these cylinders to raise and lower the platform, but they didn't want it to behave like a traditional air cylinder. Air cylinders, if you have something that's really heavy and you got to move, they either go really fast or really slow, and they typically don't do it well. So if it's like, in this case, it would be getting the platform to go down is all the energy. So as it would dispatch down and that platform would start to go down, it would take a lot of effort to push that platform down, and theoretically those air cylinders would push it and it would just go slower and slower and slower, because the only way to get it to go faster would be to turn the air pressure up. And then when you turn the air pressure up, it tends to go down really fast.
That's what she said!
And starts banging at the bottom. You flip the coin and say, hey, let's get that platform to come back up. That exact same air pressure is now assisted by the weight. And what happens is it comes up really hard and fast.
That's what she said!
And slams into the stops in the up position, making a tremendous racket. The whole station shakes. It's really bad. So what they did is they took those cylinders in front and filled them with hydraulic fluid. They ran the fluid lines out to the other side of the platform, and they gave it two really big cylinders underneath there. The cylinders are filled up about halfway, a little bit under halfway, with hydraulic fluid, but there's nothing inside the cylinders at all. It is simply just a cylinder of hydraulic fluid, and then what they did is they used air pressure on top of it. So you pretty much put the max air pressure to those cylinders and it pushes on the hydraulic fluid. There's no piston or anything like that inside. It's just air pushing on the hydraulic fluid. And then when you drop the platform or raise the platform, now we're using hydraulic fluid to do it. So we can easily regulate the flow of hydraulic fluid to get smooth, consistent cylinder operation, both in the down and the up position, making it nice and smooth. Someone sent me a video of the SLC where it was dispatching with the platform in the up position. Now, I made a response to that and I said, they're not supposed to do that. The platform is supposed to be down. Well, yes and no. So when you say dispatch the train, the platform is told to go down. Some parks out there don't do that. They just leave the platform up. They're just like, we don't care. No one's going to get hurt. It's fine. Leave the platform up. Some parks out there stay with Vekoma's original programming and say, okay, once the platform is told to go down, dispatch the train. Now, our park, we actually had a series of injuries on the platform. People were hitting their feet on it. I don't know. But people were hitting their feet on it. This was before my time. So actually when the ride was really new, they said, well, not only do we want the platform to go down and then the ride to dispatch, but we want to make sure the platform is in the full down position before the train can move. Now, from Vekoma, they had sensors to say that the platform was either down or up. They were at the very front of the platform. But they did not inhibit the train from running. That was a really odd thing. I don't know why. That was a really odd thing. Like, why would you know whether it's up or down and not inhibit the operation of the train, prevent the operation of the train? So that was really weird. But anyways, the park modified the program of the ride to say, okay, when you put the platform down, we needed to see it in its full down position, 100% down, before the train is allowed to dispatch. Now, that's one thing a handful of parks did, but not every park did. So there's a lot of variation in that. While we're talking about controls real quick, let's talk about the control system. This is a relay logic driven ride. The earlier ones are all relay logic driven rides, and they came with a PLC inside of them, but the PLC was only used for diagnostic. It was not used to actually control the ride. So when I say control, PLCs have outputs. Output turns on, something in the real world turns on as well. But in this case, what they did is they said, okay, we want the PLC to monitor all the relays. And then when relays tripped in a different position or at the wrong time, then the PLC would see that. The ride would stop operation because its relays were now out of sequence, but now the PLC would give you an error code and say, oh, the ride had this error, and then we knew what error to go look at. Kind of. Our PLC didn't work on the thing for like the first 8 years, so when that ride went down, it truly was a mystery of why it went down, because the PLC never worked. It didn't tell us what the problem was. It wasn't until 9 or 10 years after I'd been there, engineering was like, let's replace the PLC with something that we have the fault logic and everything else for, and will build its own logic. So they did that. So we got a PLC that worked again and could now communicate its trouble codes. Kind of. It didn't work well either. So for myself, that's where I got all of my troubleshooting experience from, because I had a ride that stopped working and it could not tell me what was wrong. And I had two big, huge cabinets, 8 feet tall, 16 feet long. I had 2 of those cabinets worth of relays and contactors and everything else, and the ride wouldn't work because of something. It didn't know. It just worked because of something. Let's talk about, since we're on the topic of controls, let's talk about a block check, because that has to deal directly with controls. So when you do a block check, you would send one from the station and put it up onto the lift hill. You'd bring the other train into the station and stop it. And then while the other one's still on the lift hill, you would put the platform down and then press dispatch. And that one in the station shouldn't go anywhere. That was checking block A to B. It's like, okay, there's one block check complete. You start the lift up, send the train up and over, and then you would go ahead and put platform down and dispatch onto the lift hill. So now you have one train on the lift hill, one train in the free run track. And then as the train would come through its brakes on the other side, there were control switches on the panel. You can go to the brake control and just simply turn the brakes off. And when the ride said, okay, the train slowed down, let's open the brakes, you could just flip the switch and say, nope, don't open the brakes, and hold the train in trim 1, which is what you needed to do. As the second train went up the lift hill, it would get all the way up to the very top, which is called what? That's right, Lift Park. Good job. Man, I can't believe you guys knew that. It would go all the way up to Lift Park and then stop. It's like, okay, then you go back to the control panel, turn the brakes back on, and let the train roll out of trim 1. As soon as the brakes got the command to close, you could hear them out on trim 1 just go clunk and close. then the lift would automatically start back up and send that train over. Now you have one on the free run track, one in trim 2. And you simply just wait for the one in the free run track to hit the brakes. You'd be ready on the e-stop, of course. And then once it hit the brakes, it would come to a stop. It would come to a hard stop. And then it would just sit there. And then from that point, you go, okay, open up, and you dispatch the train from trim 2 back into the station. As soon as trim 2 is cleared, it'll close those brakes and then release the brakes in trim 1. Now, the brakes have 2 different solenoid valves. It's actually 3, but they've got 2 different solenoid valves for pressure. One is a high pressure, one is low pressure. The way they are called out in the manual, they're emergency, which is your high pressure, and then your trim pressure. So as the train comes into the brake, the ride is actually sitting there on the trim pressure. Let's say it's at 40 psi. So you get a nice gentle-ish stop in the brakes. Now, a lot of people that have experience with these brakes, they know you kind of go in there and you get this real, it's like, oh, this is nice, and then at the end it's like, ugh, and you get a really hard jerk forward. Well, that's because your brake pressure is increasing. Every time the train comes into a new brake, you're stopping the train with, let's say, 1,000 psi of clamping force. Then the second brake, that's 2,000, 3,000, 4,000, 5,000, 6,000. Well, you never remove that clamping force. So it's like coming to a stoplight and putting your foot on the brake pedal, and as you come to a stop, you start to pull your foot back off the pedal to make that nice, gentle stop at the light. But in this case, what it's doing is you're putting your foot on that brake pedal, and as you come to that line, you just push harder and harder and harder until it's all the way on the floor. That's essentially how those brakes work. That's why magnetic brakes they're better. They're better for the ride, they're better for the comfort, but they are more expensive at the same time. Now, if the block in front of those brakes is still occupied, it won't bother with the trim pressure. It simply just turns on the full pressure or emergency pressure. That's the reason why normally when a train comes to stop with an empty block in front of it, it will come in almost all 10 brakes before it stops. And when it comes in with a train in front of it, it'll stop in about 4 to 5 brakes, about half the distance, really short. The main trim brake is also fixed with deacceleration sensors all down the center of it. So as it comes in, basically it starts 2 timers. One's constantly resetting and one is just watching. So the way it works is that when the train comes in, it says it can't get from point A to point B in under 3 seconds. It has to take longer than 3 seconds to get from point A to point B. So that's your first timer. Your first timer comes in as soon as the train hits the brakes. The first timer starts counting. It goes 1, 2, 3, and then it says, okay, it disables that timer because it says the brakes have been closed long enough. So it disables that timer and then looks for the trim timer. The trim timer, you could see them in the brakes sometimes. I probably can't find a picture of this or a video. I'll look for you though. Anyways, in the trim section, there's 2 proximity sensors that are only about 8 inches apart from each other. Those proximity sensors are measuring the gap of the brake fin. Now, as that gap passes by those proximity sensors, they count and they time off of the brake fin. So they have to be on and off for a certain amount of time, and then once they meet their criteria, they say, okay, the train is going slow enough. The problem is that the brake fin on top of the train is about 1.5 meters long, and the gap is only about this big between the coaches. So you have this very long space followed by this little tiny space. Those sensors that they put out there to measure the deacceleration are very far between. They're actually like 4 or 5 brake segments between. So they're measuring this uneven gap essentially all the way down. So the trim function on these rides is very tricky because it rarely ever works. Most of the time you just end up getting the hard stop.
don't think anybody actually enjoyed that.
And it's not very comfortable. Every once in a while, it slows down and then the brakes release and you get the actual trim function out of those brakes. Feels really nice. Sorry, I'm all over in the video. I know, it's just the way my brain works. All right, we've done the trim, we've done the reduction or the D-brake, we've done the station, we've done the run track. Well, we haven't done the run track, but I mean, the run track is the run track. There's not much to it. There's elements out there. People have fun. It's awesome. So let's talk about the lift hill now. The lift hill, what's different than most rides on the lift hill? Where there's two things that's different about this lift hill. The first thing is that the motor's at the very top. Why did Vekoma put it at the very top? It's noisy. So why did you put it high up for everyone to hear? Well, they didn't want it down at the base. Well, where is the base of the lift hill? It is right next to the station. So literally, if you put that motor down at the bottom of the lift hill, that's going to be really loud for everyone standing in that queue line, people loading, all that other stuff. And I don't know if you noticed or not, half the cycle of the SLC is done with the lift motor running while it's going up and over that lift hill. So it spends a lot of time on, and it is loud. So they wanted it furthest away from people as possible. So it's up at the very top of the lift hill. Yes, it is a pain in the butt to work on because you got to drag everything up to the top of the lift hill. That's no fun. The other thing that's unique about the lift hill is that it uses an anti-rollback, a cam style anti-rollback on the train. So instead of having a typical toothed rail going up the lift hill, you have just one, it looks like a giant brake fin that goes all the way up the lift hill, and that is what the anti-rollback cams grab onto. I made a video about that already. Let's take a look at that really quick. Manufacturers like to use cams. Now, you guys are going to be surprised to learn that I made this out of cardboard. I know, right? It's crazy. Never done something like that before. But anyway, so this is kind of a mock of a cam that you would find on a roller coaster. Now, where can you find cams like this? You could find them on the top of an SLC. I know I used to work on the SLCs. So you can find them up there where you have two cams like this. So you can see them there. And what they have is they have little teeth, and the reason why I colored the ends of them like that is because these teeth are typically removable inserts that come out of there. And you can put new ones in there. That way when they wear down, you can just replace them with new stuff. There's a measurement that Vekoma gave and says they can't be worn below, it was like 2 millimeters. We replaced them every year, but we took one time and ground it down to 2 millimeters. Holy crap, there was nothing left. And that's pretty amazing. Vekoma says that works with that much material missing, because it was like, whew, man, there was nothing left on those things. So the way these work is they sit here like this, and then they, either the brake fin or the fin on the track comes through and then causes these guys to open as it passes through in the center. And then what happens is that as the train stops and tries to move backwards, these guys then bite back into the rail and cause it to stop. I guess if you're looking at it this way, it would probably make more sense to do it like this. So they'd be passing by like that as the drive sword's coming down this way, and then as it tries to stop and the train rolls backwards, it essentially goes and stops. So those are anti-rollback cams used on the top of SLC. So I built up also a mock board. This one I went way above and beyond, because I not only used cardboard, but I used parts of soda cans too. Coming up in the world, absolutely. Everyone else is like 3D rendering and CAD programs and stuff, and I am like, I used aluminum cans this time. Oh yeah, that's right. Still Scotch tape down. That's what I do. All right, so we're gonna take this first one, put it on just like that. Take the second one, same thing. Put it on just like that. And now there's the opening in the center. on the SLC, there is a fin that sits right next to the chain. You don't really notice it because it's only 12 millimeters wide. And you have to look for it. Otherwise, it just blends in with everything. You don't really see that it's there. But as that fin comes up here, it hits this, and it opens these two guys up like that as it passes through. And then they're also spring loaded back down. So that would be the engaged right there. So if we spring load these real quick, hold on. I know what you're saying, and yes, I'm working on spring loading cardboard. It's only for YouTube I do the high dollar stuff like this. For your roller coaster and your amusement park, don't use cardboard parts for anti-rollbacks. It doesn't work good. I don't recommend it at all. So if you're working on a real roller coaster, please don't use cardboard. Because if I get pulled into court and you guys are like, Your Honor, the guy on YouTube told me to use cardboard to make anti-rollbacks, so I did. Hey, check that out. Spring loaded now. Here is my fin. We'll call this right here. So my fin will come up right through here, and I'll push it straight up between these two cams. And then as I try to pull backwards, I can't. It stopped. It's actually... Hey, check it out. I just made a cardboard anti-rollback. And it's working. Surprising, right? But you can see that from there. So as I push that fin up and try to pull it back down, it stops because those cams are just minutely letting the fin pass through, and then it stops again. Now, this is the reason why on the SLCs, when you hear them going up the lift hill, if you pay attention, it sounds like there's metal dragging, because it is. As you're going by, as this fin's going by, it's dragging through those cams. And then every day it's important that we have to get up there in the train, and then we have to check and make sure the cams are free moving, you know, that you could open them both up like that, and they spring back on their own, and they meet back somewhere in the center. The cams find their own center, because even if I left them like this and then I sent the ride out the first time, the brake fin will come back in, or the anti-rollback fin will come back in, and it will naturally just find its center again as soon as it opens the first time, and then it stops. So that is the basic cam design that you find on top of SLCs. So this is mounted in the train of the SLC. In fact, if you're sitting there, wear it like a hat. If you're sitting there in the train, this guy sits on the left-hand side right overhead like that. That's where it is. Interesting stuff, right? Okay, so keeping with the lift hill, let's talk about evacuation, because the evacuation pretty much touches all aspects of the ride. So because the trains are underneath the track, you have to have special equipment to evacuate from. Now, the first couple of models that were released were not great. They did not have a good permanent method to get people off of the train. So typically around these rides, you have a man basket or a man lift parked there in case the train stops on the lift hill and they can't get it restarted. They have a man basket there to take people off. Yes, that's got to be a scary process for most people. Most newer rides, they actually have a staircase that goes up there, and underneath the staircase there looks to be a square trellis underneath there. That trellis is actually holding a evacuation platform that sits all the way down at the bottom of the lift hill, and that platform can raise up alongside those staircases, and then has a square platform that simply stops underneath the train, and you can get the people off that way. Now, the restraints open with power, so you need 24 volts. There's a battery box, typically 2 battery boxes at the ride. that are charged, ready to go for when you need to do an evacuation. You simply plug the battery box into that particular row, press the button, let the people out of the restraints. Not really a big deal. All that emergency stuff is operated off an emergency generator. Now, ours had the emergency generator. I could see some parks not wanting to put that in, but ours had the emergency generator, and it ran two things on the ride. It ran the lift hill. So up on the lift hill at the very top, there is your main DC motor with a very large planetary gearbox right there that turned the chain. Nothing special about the chain. It's just a standard straight link chain. I believe it's a 5.5-inch pitch Reynolds chain. Nothing special about it. But before that DC motor got to the planetary drive, there was another gearbox right there that had a T on it with a smaller motor. And the smaller motor was the emergency motor. So the emergency motor was what you could turn on during some sort of a power outage. Now, the main purpose of the emergency motor was actually just to get the train off the lift hill. And it says very specifically in the manual, big warning about it, not to use the emergency motor to push a train full of people over the top. Once you got the ride into the emergency function mode, you killed every aspect about it. You were simply operating the ride with the emergency motor now. Like literally, I can go up there and turn that motor on with the generator running and send the train over. It's a very slow process. It takes a long time to do because the train doesn't even go at a crawl. It goes a very slow speed up that lift hill. But if there's no brake pressure down below, I can send the train over. If there's another train right in front of it, I could send the train over. I could do all sorts of stuff like that. So Vekoma's, what they really stressed in the manual was never operate emergency functions with people on the ride. Safest thing to do, just don't do it. The other part of the evacuation is down in the brakes. Sometimes you had to take people out of the brakes because you couldn't advance a train into the station. It was a rare thing, but it happened from time to time. So what we had in there was the same man lift or scissors lift that we used to inspect the brakes in the morning time was also used for the evacuation process. It wasn't until many years later we actually built a platform underneath the brakes so we can actually go up there and service the brake assemblies without having to need the man basket or a scissors lift or anything else. And it could, in a pinch, also be used for evacuating the train. Okay, so let's move on to the train itself. Most SLCs use a 10-coach train, although in the manual it says it right there. My train had 10 coaches on it, and the manual said some of them have 7 to 10 coaches. So it's like, okay, 7 to 10, there's a range depending on the park, the design, whatever it may be. 7 to 10 is your range. That is 10 coaches where you can sit. And the SLC used a tail coach, like B&M uses a pilot coach or a zero coach. That's the same thing with a lot of Intamin rides. They use a zero coach. Well, the Vekomas used a tail coach. This is what they used on the SLC. They also did the same thing on the Boomerang as well. They would go 10 coaches where you can sit, and the 11th didn't have a set of seats on it. It simply was just the main axle housing that sat up there. The main axle housing, wheel carriers, brake fin, nothing else. It was simply just the back end of the train to hang on for the rest of the assembly. The coach construction was fairly simple. It was made up of a main axle housing, which held 2 wheel carriers. Each wheel carrier had 5 wheels on it, which is not typical these days. These days you have 6 wheels, but those had 5 on them. You had 2 road wheels, 2 guide wheels, 1 upstop wheel. Now, 2 road wheels to 1 upstop wheel, this creates a triangle, and this is the reason that the ride is one of the reasons why the ride is so bumpy, is this triangle setup on the road wheel and upstop wheel. There's a lot that goes into that, and I don't know if this is the video to get into it, but that is one of the main reasons why the SLCs are so bumpy, because of that old triangular wheel setup. They're not great, and it's compounded by issues in the track as well. Okay, So we move along from there and go down. Now they have what's called a backbone or a seat hanger. The backbone is a piece that comes down from underneath the fiberglass cowling, which covers all the wheels up so you can't just reach up and stick your hand into a wheel. That's the fiberglass cowling. And the backbone comes down and branches off and holds 2 seats. The seats are really simple in their construction. They simply have a back and a bottom. And then they've got these 2 little, it looks kind of like handrails on both sides, these little handrails that look kind of like an oval shaped thing. And people think, wow, that's really weird. Why would you hold on to those right there? They're not for holding on. They're actually the lateral supports that help keep you in the seat. So a lot of people think they're handholds, but they're not. They're lateral supports. You have an over-the-shoulder restraint with a little set of handlebars in the front to hold on to. In the back, there is not 1 ratchet assembly, but there is actually 2 ratchet assemblies in tandem right next to each other. And those are locked in with 4 paws, 2 on each ratchet assembly, 1 on the left side, 1 on the right side. Those are unlocked by an electric actuator. This was one of the causes of so much downtime for these rides because that electric actuator needs a lot of adjustment and it's got to be dead on balls accurate, perfect. It's got to be right there in order for it to work. If it opens up, as it opens up, it unlocks all 4 teeth. As it locks back, it simply closes and the teeth are spring-loaded. They go back into the shaft on itself. So Vekoma says when it's closed, it can't be gripping the assembly. It can't be holding that assembly because that could cause bind and cause the restraint assembly not to work. Now, these little actuators, when they open up and unlock the assembly, they also have to be loose side to side there as well, because these things are so powerful that if they open up too far, they will break the restraint components. These things are really powerful little things. So everything's got to be done perfect inside there for all that to work. And then once those little teeth are down and closed, each time one locks in the closed position, you have to maintain a 2 millimeter air gap between the restraint component and the teeth on the inside. It's like, ooh, yeah, so much time spent in my life making those restraints work. There was a lot of adjustment to them. Almost everything inside was adjustable and not in an easy way. There was like all the movements compounded off of each other. So if you got one thing wrong, it messed up a whole bunch of other stuff. And then at the end of that actuator, as the actuator extended all the way out or into the closed position, there was a mechanical limit switch at the end that said it was close. Again, so much downtime on this thing because what happens is that mechanical limit switch says I'm closed. That actuator is closed. Well, there's 1 per seat, 20 seats in the train. Well, they daisy chain the signal. Again, it comes from the ride, 24 volts. It goes into the train and goes through all 20 of those and then goes back out to the ride and says, okay, the restraints are locked. The ride doesn't know the restraints are locked because when you lock the restraints, all of them are in their full open position. And it's like, restraints are locked, you're good to go. It's like, restraints are still open. They may be locked, but they're still open. So what would happen is that they would close all the restraints, do all their pre-checks, and go, okay, dispatch. They would go to put the platform down. Platform wouldn't go down because it said the restraints are unlocked. So it's like, okay, we can't do that. So operations had to unlock all the restraints and recheck them again and lock them back. And if it did it again, then they'd have to let everybody off the train and call the ride down because they're like, we can't dispatch this train. Now the people in the trim brakes that are waiting from the ride that just happened, now they are stuck there because operations can't get the train in the station out because the ride doesn't know that the restraints aren't locked. So it's like, ooh, that was a troublesome call. It happened up all the time. So a supervisor and I got together, and he came up with an electrical modification for the train, which allowed us to check where those restraints were, where that thing was open in the train. It was a very complicated system, but we got it down. We were able to plug a little pendant into it, and we were able to check and say, okay, basically we had to start where the pickup was, which was coach 7, and then we plugged the pickup in there, and then we can tell whether there was an open signal in the front of the train or towards the back of the train. So it was like a fork check, is it towards this way or this way? That way. It's like, okay. Then we had to go to the next coach in front, plug it in. Now, if we looked backwards, we would see the pickup, so we couldn't look backwards. We always had to look forward. So we go, okay, look forward. Is it still open? Yes. Okay, go to the next coach, plug it in. Look forward. Is it still open? Yes. Next coach, go forward, plug it in. Is it still open? No. It's like, okay, and then on that coach, we had another check. Is it the left seat or the right seat? Right seat. It's like, okay, we got it. Now, these days, most people don't have to worry about that because the rides power up sensors on the inside, and a lot of rides now use ASI or smaller PLCs inside the train to actually tell you where the erroneous signal is inside the train. Then the computer will know at the operator panel. They'll tell you, like, oh, hey, restraint number 14 is not locked. It's like, oh, okay, well, let's go fix restraint 14 then. But this older stuff, old problems, again, newer trains probably got PLCs in them too. I'm sure Vekoma does that because they're good about that stuff now. But the older stuff, we had some issues with some things. Like, again, that was my primary ride. I spent a lot of time working with it. So that's one of the reasons why this video is so long too. All right. Top of the train, each coach has a big brake fin. These are big steel, looks like a steel plate sitting up there, 15 millimeters wide. Oh, wait, no. Things, yeah, they're roughly about 15 millimeters wide, and they had to be replaced once they were worn down to about 10 millimeters. The main axle housing was joined with a very large pin in the center that allowed the main axle housing to pivot left and right to follow the track. Well, the bushings and everything around that pin, that stuff wearing would loosen up and cause the backbones, the seat hangers where you sit, to shake back and forth, which also created a very rough and uncomfortable ride. Not easy to tighten. Every time we ended up tightening one of those things, it was basically the night shift would have to start it, day shift would have to finish it, and the ride typically opened up late, and that was just to do one of the 10 coaches, and they loosened up all the time. Big pain in the butt. I know Vekoma's fixed a lot of that stuff. This is in the past stuff that I'm talking about. Not too crazy. Chain dogs. 2 chain dogs. One around coach 5, and then one on coach 7. The chain dogs, this is one of my mocks that I made up of it right here. This is essentially kind of what the chain dog looks like out of there. It's got the pivot pin right here, and it sticks up into the chain like this. Now, alongside, there is a spring that's mounted right here, and that pulls really hard, and it pulls tension, and then this guy lifts up like that. And then it's spring-loaded up from there. So, chain dogs, nothing too fascinating to look at, but that's pretty much what it is right there. We already went over the anti-rollback cams, because the cam anti-rollback style, there's 3 of them. So the chain dog was on 5 and 7, but the anti-rollbacks were on 6, 8, and 9. They were on those coaches. So everything towards the back, typically the first 4 coaches are blank on the ride. They had nothing on them. And then coach 7 also had the pickup trolley, which communicated that the restraints were closed, and it also received the power to open the restraints and close the restraints. Now, one of the rough things about this ride, remember how I was talking about the wheel carrier with the 2 road wheels and the 1 upstop wheel? Well, when you take a rail and you bend it downward, the distance between those 2 points gets larger. And when you bend it the other way, that distance gets smaller, it goes to non-existent. So what you have to do for that upstop wheel is you can't run the upstop wheel up against the rail. You actually have to run it further away from the rail to allow for the thing to twist up like that. So between the road wheels and the upstop wheel, there is supposed to be a 2 to 4 millimeter gap on that. Well, if you look at that 2 millimeter gap, let's just say, and you stretch it across to about 1200 millimeters between the rails, 12 to 15, no, about 1200 millimeters between the rails. And then you say, well, that's 2 to 4 millimeters that can shift upwards on one side. Well, that means that you are sitting roughly 2.5 meters below the rails. So when that 2 millimeters shifts up like that, you swing out to one side, and that is not comfortable. That's one of these reasons the rides is so bumpy, because that thing is constantly dancing left and right like that and jumping up and down. The wheels aren't spring-loaded to the track. They're not tight at all. It's the same thing with the guide wheels. Remember how I said at the beginning that the C-shaped rails like this, where the train runs on the inside, it's an older style. Well, when the rails squish together and come apart, you can't really let the train run through that because it can't go negative. So you have to space the guide wheels further in on the assemblies as well, which means now there is space to go left and right, and the train just drifts. It's actually supposed to be about 3 millimeters on each side. So you have 6 millimeters that the train drifts left to right, and you have 2 millimeters to 4 millimeters on each side that the train can jump up and down. The backbone that holds a seat has 2 big shocks on it too. Those shocks don't really move. They are very solid, but they do under lots of G-force. Again, it's everything wiggling. It's like the shocks, the vertical center pin, the guide wheel clearance, the upstop wheel clearance, and then the track. The track has round rails, right? No, it doesn't. It doesn't have round rails at all. So the rail starts round, and then when they bend the rail to go up, down, left or right or whatever, as they bend it, they squish the rail. So as it's going up, the rail squishes down and turns oval. As it's bending hard to the side, it goes vertical and it squishes this way. So the rail dimensions are always changing everywhere too. Now, they offer track straightening for stuff. It doesn't really help much. The company invested a bunch of money in track straightening for the ride because they did a VR overlay on it, and it's just like you could barely feel the difference. You could see it on an accelerometer test. We had engineering, they brought accelerometers in and we tested before and after. You could see the difference on the accelerometer, but actually riding it, that was a lot of money with hardly any outcome from it. That wasn't great at all. So in the wheel carrier, there is so much play in all that stuff. Not to mention the axle housing itself has just a little bit of an assembly with some rubber elasto bushings on both sides that allow the axles to pivot up and down. So I mean, the suspension on the train mixed with the track becoming different shapes, mixed with the 5 wheels instead of 6 with air gaps everywhere. It's one of the reasons those rides are so bumpy. And that's where we get the phrase that, you know, people that want to ride an SLC haven't ridden an SLC. that is one of the things that happens with those. Troubleshooting and stuff, man, I've spent so much time working with the restraints. That's almost always where the problem is with that ride. It's in the restraints. Very early on when I first took over it, Vekoma was using a simple spring pin that was holding the restraint shaft and the little ratchet dog together. These are the 4 ratchets I was talking about in the restraints. They were using a simple spring pin to hold that assembly together. Well, those spring pins would break all the time. We used to have, like, the primary mechanic and myself, before I was the primary mechanic, we would carry these rescue kits with us. It was all the tools we needed to quickly take apart those restraints, because what would happen is they would come back in and they would open the restraints up and someone would go, oh, my restraint's not opening. And operations would come by to give it the little jiggle and let them out. It wouldn't open up. Those people were stuck there because in the back of that seat, 1, 2, 3 unlocked, and that fourth one was, that little roll pin was broken and that tooth was just stuck in there. There was no way that thing is coming out. So we had to go there really quickly. We had to take out our little rescue kit and we pull the seat back off real quick. We go, which one is it? It's this lower corner right here. So we'd have to take the hardware apart on that real quick, go over. And then part of our kit was we carried 4 flathead screwdrivers around, because once we pulled the actuator back, put 2 flathead screwdrivers in this side to open the springs on that side. So you had to put your arm up there to open those 2. And then we put in another flathead screwdriver to open, like so in this case it was the top side, so you reach over and grab that and you pull that back over. And then that third one that was down there, that last flathead screwdriver, you had to push it in there, and then it's kind of like a locksmith. You had to feel for it and just barely get it to catch the tooth and start twisting it back apart, and then the restraint would open, the people would get out. The fun part about that is we always got a good round of applause for that. Everyone would burst out cheering when we finally got that person out of that seat. But that was only part of the trouble call, because now we had to get that train out of the station because the other one still has 20 people stuck in it. So it's like, get that other one in here, get that unloaded, then that first one comes back, and then we'd have to call the supervisor. Wasn't me at the time because this is early in my career. And say, okay, what do you want to do? Do you want to tag this seat out or fix it? And then that was always a judgment call depending on the day, how busy the park was, how busy the ride was, all that stuff would make the determination if we wanted to just tag the seat out or try to fix it. Operations had a say in it too, but most of the time it was our call to repair the units. I have had one of those calls before too where I got someone out of the seat. Cool. Got the train out, brought in the other train, and wouldn't you know it, the exact same thing happened on the other train to a different seat. Could not believe it. I think that happened one time to me, where I had to get 2 people out from 2 different trains on the exact same ride call. Lots of paperwork to explain that stuff in the background. Refurbishment on these trains is nothing mind-bending either. It's typically replacing all the bushings is always a thing. It's replacing the bushings, trying to make sure they're as tight as you could get them before you put the train back together and put it in for another year of service. Those bushings would always wear out pretty good. It wasn't a lack of grease or anything like that. It was just the nature of the ride. They would just get hammered and oblonged. And then it was also the nature of assembling sometimes. Like we had lots of hammer mechanics instead of measuring mechanics, and they would hammer bushings in. What happens when you hammer a bushing in? Well, you give it a lip. Like it creates a mushroom lip on the outside. So you have to go through and machine that lip back out. And then by the time you're done doing that, you've now messed up the rest of the bore too, and the pin just falls into the hole instead of pushing into the hole. So if you're not there already, please don't hammer bushings into the bore. Please use something like threaded tools to draw it in or hydraulic assembly tools to pull it in. Please don't hammer bushings in the bores. It's not fun for anybody. Alright, this has been a very long video. Just all the time I've spent taking care of an SLC. I just wanted to put some of that out there. Like and subscribe, do all that stuff downstairs. I do appreciate it. If you want to contact me, you can contact me at ryantheridermechanic@yahoo.com or simply just leave a comment downstairs. That always works too. I pretty much read everything. I may not respond to everything, but I pretty much read it. And let me know what you think. What's your experience with the SLC? Do you enjoy them? Do you not enjoy them? I mean, if you made it this far in the video, you probably enjoy them. Or you fell asleep. Did you fall asleep? Probably fell asleep. Maybe we should just let it run. Play goodnight music. Oh well, maybe not. I'm Ryan the Ride Mechanic. Stay off the air gates.